this video, we are going to explain about the project title T-YOLO, Tiny Vehicle Detection based on YOLO and Multi-Scale Convolutional Neural Networks. Introduction. The project's focal point is the detection of vehicles within expansive parking areas, specifically highlighting the challenge of accurately identifying available parking spaces among the parked vehicles. This emphasizes the difficulty in differentiating between occupied and vacant parking spots within these large parking zones, a task crucial for effective parking management systems or guidance. T-YOLO seeks to improve the detection of small vehicles by integrating YOLO, You Only Look Once, a fast object detection algorithm with multi-scale convolutional neural network CNN. This fusion aims to elevate the model's accuracy in recognizing and pinpointing tiny vehicles across various environments or scenarios, potentially addressing limitations in detecting smaller objects that standard YOLO models encounter. The obstacle faced by conventional detection models lies in accurately identifying small vehicles within intricate scenes. The complexity arises due to several factors such as the diminutive size of these vehicles, their diverse orientations, and potential obstructions or overlaps with other objects. These challenges significantly impede the accurate identification of these tiny objects by traditional detection algorithms. T-YOLO's approach involves modifying the YOLO architecture by integrating multi-scale CNN. This adaptation enhances the model's ability to capture and interpret features across different scales, refining its capacity to precisely locate and distinguish small vehicles. By leveraging multi-scale CNN, T-YOLO aims to overcome the limitations of standard YOLO models in effectively identifying and localizing smaller objects within the given scenes. Objective. The primary aim of the project is to notably enhance the precision of vehicle detection, especially concerning small vehicles within expansive parking areas. This emphasis addresses the challenge of accurately identifying and differentiating these smaller vehicles among larger ones within such environments. Through the utilization of YOLO-based models and multi-scale CNN, the project targets the improvement of current methodologies by specifically tackling the accuracy limitations present in detecting small vehicles. This approach intends to overcome the hurdles faced by existing methods when identifying these diminutive objects. Within the YOLO framework, the project explores advanced techniques including different versions of YOLO v5, SMLX, and incorporates multi-scale CNN. These sophisticated approaches aim to elevate the capabilities of vehicle detection significantly, utilizing various model sizes and multi-scale CNN to enhance accuracy. The project's focus centers on refining and adapting the YOLO architecture to better address the challenges associated with detecting small objects. Modifications within the architecture are intended to optimize the model's ability to accurately detect and localize tiny vehicles within complex scenes. The primary objective is the evaluation and optimization of different YOLO v5 variants, specifically focusing on their effectiveness in detecting small vehicles. The project aims to achieve a notable high mean average precision (MAP), indicating superior accuracy in precisely identifying and delineating these tiny vehicles within the dataset. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing necessary libraries and packages required for the project. It typically includes importing machine learning frameworks like TensorFlow or PyTorch, image processing libraries such as OpenCV, and other relevant tools for data manipulation and model implementation. Exploring the dataset. pk-lot dataset refers to the dataset used for training and testing the model. It's essential to understand its structure, contents, and annotations. Reading the image involves code to load images from the dataset into memory, enabling the model to access and analyze the visual data. Plotting the image. Visualization is crucial for understanding the data. This step includes displaying or visualizing images from the dataset to gain insights into the nature of the data and verify the correctness of the loaded images. Image processing. Converting to blob object. Blob objects are structured image data representations required by certain deep learning frameworks. This step involves converting the loaded images into the suitable format for model input. Defining the class. In object detection task, defining classes refers to specifying the categories or types of objects the model aims to identify. For example, in this project, it includes classes like car, truck, or specific classes for tiny vehicles. Declaring the bounding box. Bounding boxes are rectangular boxes around detected objects indicating the location within an image. Defining the bounding box involves specifying coordinates or dimensions that encompass the identified objects. Converting array to a NumPy array. NumPy arrays are fundamental data structures in Python used for numerical operations. This step involves converting processed image data into NumPy arrays, enabling efficient manipulation and integration with machine learning models. Loading the pre-trained model. Reading the network layers. This step involves loading a pre-trained YOLO-based model which likely contains several layers such as convolutional, pooling, and detection layers. Reading these layers set the foundation for modifying or fine-tuning the model for the specific task of tiny vehicle detection. Extract the output layers. Within a neural network, the output layers are responsible for producing the final predictions. Extracting these layers allows for customization or integration with additional layers tailored to detect tiny vehicles accurately. Image processing. Appending the image. Annotation file and images. Combining image data with associated annotation files, if available, creates a unified dataset where images and the corresponding labels or annotations are linked. This step is crucial for supervised learning tasks. Converting BGR to RGB. OpenCV typically loads images in BGR, blue, green, red format, while most deep learning models expect images in RGB, red, green, blue format. Converting the image format ensures compatibility with the model. Creating the mask. Masks are binary images used to identify regions of interest or specific features within an image. In the context of creating masks involves highlighting areas where tiny vehicles are expected or defining regions for detection. Resizing the image. Resizing images to a standard or model compatible size is essential for consistency and efficient processing. This step involves adjusting image dimensions to match the input requirements of the neural network. Data augmentation. Randomizing the image. Applying random transformations or augmentation such as flips, shift, or brightness adjustment to images diversifies the dataset, reducing overfitting and improving model robustness. Rotating the image. Rotational augmentation involves rotating images at various angles, providing the model with variations of object orientations, enhancing its ability to detect objects from different perspectives. Transforming the image. Image transformations encompass a range of operations like scaling, shearing, or perspective changes. These alterations create a more comprehensive dataset, aiding the model in learning from diverse data representations. Installing the packages required for YOLO, Wi-Fi, and Collab. This step involves setting up the necessary environment in Google Colab by installing specific packages, dependencies, or frameworks required to implement and execute the YOLO v5 model. Processing the data based on YOLO v5 model. This likely involves additional data pre-processing steps tailored specifically for the YOLO v5 architecture, ensuring compatibility and optimal input format for the model. Building the model in Colab. Creating or configuring the YOLO v5 model architecture within the Colab environment, setting up layers, configurations, and connections required for subsequent training. Training the model. The model is trained using the prepared dataset and the YOLO v5 architecture, iteratively adjusting its parameters to optimize for the task of tiny vehicle detection based on the dataset annotations and images. Flask framework with SQLite for sign-up and sign-in. Flask is a web framework in Python used for building web applications. Incorporating Flask suggests the creation of a user interface where users can interact with the model. SQLite for sign-up and sign-in. SQLite is a lightweight database often used for small-scale applications. Implementing sign-up and sign-in functionality using SQLite and Flask allows users to create accounts and log in securely to access the application. User gives input has image or video. This module involves creating an interface within the Flask application that enables users to input either images or videos. This could be through file upload functionalities or other input methods provided within the interface. The given input is pre-processed and with trained model is used for detection. Once the user provides an image or video, the input data undergoes pre-processing steps similar to those used during the training phase. This ensures compatibility with the model's input requirements. The pre-processed input data is then fed into the trained model, which applies the learned detection mechanism to identify tiny vehicles within the provided image or video. These segmented each object and put bounding box. The model's output includes detected objects, likely represented as bounding boxes around the identified vehicles. Segmenting involves precisely delineating these objects within the image or video, while bounding boxes indicate their location and size. Final outcome is displayed. Finally, the detected tiny vehicles along with their bounding boxes are displayed to the user through the Flask web interface. This provides a user-friendly visualization of the model's predictions, enabling users to view the identified vehicles within the uploaded image or video. Algorithms used. In this project, we have utilized the following algorithms: YOLO v5s, YOLO v5m, YOLO v5l, YOLO v5x. These variants represent different scales or sizes of the YOLO v5 model. They vary in terms of depth, number of layers, width, number of filters, and overall complexity. YOLO v5s typically refers to smallest or smaller version, while YOLO v5x represents the largest or extra large version. Models like YOLO v5m and YOLO v5l fall in between, offering a trade-off between speed and accuracy. These variants enable the project to test and compare the performance of YOLO v5 at different scales, selecting the optimal balance between speed and accuracy for tiny vehicle detection in various scenarios. YOLO v5 MSM Multi-Scale Model. This variant indicates a YOLO v5 model architecture specifically designed to incorporate multi-scale features. It likely integrates mechanism to extract and process information at multiple scales within the network, aiding in better feature representation and object detection. The inclusion of multi-scale capabilities enhances the model's ability to detect tiny vehicles across different sizes and orientation within the dataset. YOLO v5 MSM and CAM. Class Activation Mapping. Class activation mapping is a technique used for visualizing and understanding the areas within an image that influence a specific class prediction made by a neural network. Combining CAM with YOLO v5 MSM involves incorporating CAN mechanism into the model architecture. This integration allows the model not only to detect objects but also to provide insights into which parts of the image contribute to its classification decisions, aiding in interpretability. YOLO V-File SMX. This variant signifies a specific configuration or modification of the YOLO V-File model tailored for enhanced performance in detecting tiny objects. It includes unique optimizations, architectural adjustments, or additional features that aim to improve the model's sensitivity and accuracy specifically for tiny vehicle detection tasks. These variations within the YOLO V-File framework offer different trade-offs in terms of speed, accuracy, and computational requirements. They provide flexibility in choosing the most suitable model architecture for detecting tiny vehicles based on the project's specific needs and constraints. Models are compared with the parameters precision, recall, and MAP. This is the precision comparison graph. On the x-axis we have precision score and on the y-axis we have algorithm name. Precision is the ratio of correctly predicted positive observations to the total predicted positive observations. In the context of object detection, precision measures the accuracy of the model in identifying relevant objects. High precision means that when the model predicts an object, it's very likely to be correct. This is the recall comparison graph. On the x-axis we have recall score and on the y-axis we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the ratio of correctly predicted positive observations to all actual positives. High recall implies that the model can identify most of the relevant objects in the dataset. This is the MAP comparison graph. On the x-axis we have MAP and on the y-axis we have algorithm name. Mean average precision is a metric that combines precision and recall across multiple thresholds. In object detection, it measures how well the model performs in detecting objects at various levels of precision. MAP is calculated by taking the average precision across different recall values. It's commonly used to evaluate the overall performance of an object detection model. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address. This localhost and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up. So here we need to enter all these details to register. But I have already registered, so click on login. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So here we need to upload the image. Click on choose file. I'm selecting the first image. Now click on open. Now click on upload button. So here we can see this is the parking area and the application has detected the occupied and non-occupied parking slot with the bounding boxes and differentiated them with a different color shade, and we can also see the probability score of the detection. Now let us upload one more image. Now click on choose file. So here I am selecting this image. Now click on open. Now click on upload button to detect the small and tiny vehicles in the parking area. So here we can see the application has detected the occupied and non-occupied parking slot with the bounding box and differentiated them with a different color shade, and we can also see the probability score of the detection. So here we can see these are the non-occupied spaces and these are the occupied spaces. So in this way, we can detect the small and tiny vehicles in the parking area. Now click on sign out. The conclusion of the project is the project achieves substantial progress in accurately detecting small and tiny vehicles within parking areas. This accomplishment is crucial in addressing a significant challenge encountered in parking management system, where identifying these smaller vehicles among larger ones is pivotal for efficient parking guidance and allocation. Through rigorous experimentation and analysis, the project demonstrates the effectiveness of leveraging YOLO v5 variant and multi-scale CNN architectures. These models significantly enhance the accuracy of detecting tiny vehicles within parking areas. YOLO v5 variants, with their different scales and complexities, along with multi-scale CNN, proved to be instrumental in achieving improved detection capabilities for these smaller vehicles. The conclusion of the project highlights several potential directions for future research and improvements. This includes exploring additional data augmentation techniques to further diversify and enrich the training dataset. Fine-tuning model parameters could optimize the performance of the detection system. Additionally, integrating real-time capabilities into the system could be beneficial for dynamic parking management scenarios, allowing for immediate and responsive decision-making based on current parking conditions. These suggestions pave the way for continued advancements and practical implementations in the field of parking management and vehicle detection.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.